All righty, there we are. Good morning, lads and ladies. Welcome back to Calc 2. Today, we are going to change tack just a little itsy bitsy bit. This, of course, is a calculus class. We've been doing lots and lots of calculus. Today is going to be, I know, pretty much all algebra. So sometimes that's something that we breathe a sigh of relief, algebra instead of calculus. I have a feeling that's not the impression you're going to come away with from today. But of course, it varies depending on how you feel about algebra compared to things like trigonometry and calculus, which we've been doing oodles of lately. So today, pretty much no trig, very little trig, not a whole lot of calculus, but lots and lots and lots of algebra, because what we're going to be talking about is partial fractions. So let's get into it. It's a big one. This is MAC2312, section 004, which is Calc 2. And the date today is January 31st, 2022. As I mentioned, the topic for today is partial fractions. And this is a topic where you can actually go pretty deep if you want to. If you want to understand like why this works, why the setups are the way they are, all of that is stuff that you can explore to some considerable depth in a class called Linear Algebra, MAS 4105, if you go to UF. We used to do an honors version of Linear Algebra here as a 2000 level class from time to time. This section number in your book is 7.4. And this is the last section where we're going to meet new content before exam 1. So this is the last bit of new mathematics you're going to need to learn for test 1, which means I should talk a second here about test 1. So we did this a little bit already. Exam 1 is 1 week from today. Which means it's next Monday, which I believe is the 7th. Let's triple check that date. Yeah, of course. And I've released the study guide. And listen to what I say carefully here. In order to get credit for the study guide, I want to remind you, 25 points are allocated to each study guide, which is 1/4 of the value of the test. In order to get the grade for the study guide, the grade's listed here, right? The 25 points each for the study guide. In order to get that, it is not sufficient to complete the thing in WebAssign. So the study guide is posted to WebAssign because that's the easiest way for me to just give you a problem set. But to get credit for the study guide, you must submit written work for all study guide problems. The way you're going to do this, you've got several options. It's up to you. You can use on your phone an app like Cam Scanner or Adobe Scan. If you don't have a physical scanner, then you have to upload the scans to the assignment Study Guide 1 in Canvas. So if you solve the problems in WebAssign, but you do not give me your written work, then you'll get a 0 on the study guide. You don't want that, right? So in order to get the grade for the study guide, in order to get those 25 points, you need to solve the problems on paper, scan that work. You can use a physical scanner if you have one, of course, that's very nice. If you don't have a physical scanner, these two apps are free and they work well. More people have been using Adobe Scan lately than Cam Scanner. I think Cam Scanner changed to where if you don't have their paid version, there's like a finite number of scans you can do or something like that. These will both take very good scans, and you need to upload those scans to Canvas. Taking a picture with your phone is not going to work, right? I won't grade a JPEG of, like, or HIC files or anything like that. You need to give me the scans as PDFs. Scans must be uploaded to Canvas. So please don't email them as PDFs. The good news here, right? So I know that's a bit of a hassle, but this is the only way I can have you guys turn in work in this setting, the hybrid class setting. So if you have an iPhone, then you can use the Notes app also to scan and produce PDFs. You can just Google how to do that. It's not complicated. That works really well. If you have an Android, these apps work well. You can also use these apps on iPhone. If you have a physical scanner, you can use that, of course, but I need PDFs of your work uploaded to Canvas. The assignment is Study Guide 1. It's not hard to find. Just go to our Canvas class, go to assignments. The first thing you see here is Study Guide 1, right? Second thing you see is Study Guide 1. So you'll come in here and you will upload your file. It has to be a PDF. Do yourself a favor. Please don't take a picture like a JPEG or HIC picture and then use one of those tools to convert it to a PDF. That shit is ugly, dude. The whole point of having you use an app like this or the Notes scanning utility in your iPhone is to get a good high contrast thing that looks like it came out of a scanner so I can read it. So taking a photo and then using an online converter to turn that into a PDF is not a good move. One, it takes more time than doing either of the things I'm proposing. Two, it gives me a crappier quality thing to look at, and I'm going to go in there with an iPad and I'm going to mark it up the way I mark the tests. The last thing you need to know about the study guide is that the study guide is graded for completeness, not correctness. So as long as you have attempted each of the problems in the study guide, I think there are 13 problems in the study guide. As long as you have something for each one, you're going to get full score on the study guide. You're going to get 25 out of 25. What I really don't want you to do is look up solutions and write down a solution that you didn't come up with. The point of the study guide is for you to show me your best attempt at solving these problems on your own. And then I will go in there and mark not all of them, but a few of them the way I mark an exam question. And that way you'll get to see how I grade. I will get to see how you work. And those are two things that are really nice coming into the first test. You want to know how I grade, and I want to know how you work. Knowing how you work and what your handwriting is like and notation you use and all of that will help me find partial credit for you on the test problems, which is good. You want that. Seeing me mark up some of your problems the way I would mark them on the test will help you figure out what you need to change on the test. This is due at the start of the exam. That's the latest you can turn it in. Of course, you should turn it in ahead of time, right? So the very last moment I will accept the study guide is at the start of the test. You can submit your scans in Canvas up to that moment. If you submit them at that moment, then I will not be able to get in there and mark it up and give you feedback before the test. So what you really want to do is start on the study guide problems like today, tomorrow, whatever. Try to finish them before Friday. Then upload them on Friday so I have the ability to get in there, mark them up, give you some feedback before the test next Monday. All right. But if you don't want feedback for whatever reason, you're like, I'm 100% confident, I know exactly what I'm doing, I don't need to know what this guy has to say about my work, then yeah, sure, turn it in on Monday, turn it in at the start of the test. but I think pretty much everybody would benefit from this sort of feedback. Little side note, the average on my first Calc 2 exam last semester in the fall was 43%. Ouch. And it wasn't a hard test. It was actually an easier version of an old test that I'd used. The reason that average was so low is because not many people availed themselves of this system. A lot of people were under the impression that they were doing everything right, but they weren't. They had been using a lot of Mathway and Wolfram and Photomath and whatever to get through their homework. And then when it came time to actually do the problems 100% on their own during the test, they were in really bad shape. So treat the study guide like the test. Go in there, solve the problems. If you get something wrong, that's okay. But give me that work, right? Correct or incorrect, give me that work so I can mark it up and show you where things went wrong and show you how to fix the mistakes that you're making. That way, when it comes to the test, you won't make those mistakes, right? That's the way to do it. And remember, you don't need to worry about mistakes. I'm not going to take off any points for mistakes on the study guide. I'm going to give you full credit on the study guide as long as you have attempted every problem. I just want to see what you're doing and how it's going so I can give you some feedback before the test because I want your test to go well. The exam is going to be during class time, so you'll have 75 minutes for the test. So there's a DM asking how long is the test going to be? The test is going to be 75 minutes, right? So we'll start right at the start of test. I'll open up the class a little bit earlier than normal so you guys can come in and get set up, and then the test will be exactly as long as the class period. Any questions about exam 1 or study guide 1? What you need to do, how to do it, when it needs to be done, any of that stuff? How many problems on the test? Probably about 14, 13, 14, somewhere around there, just like the study guide. The test will have some true false, some multiple choice, and some free response problems. And the free response problems, you will be showing your work. And the way you're going to do that is the same way you do on the study guide. You'll take the test. As you go through the test, you will write out your solutions for the free response problems. Then as soon as you finish the test, you will use CamScan or Adobe Scan to scan your written work and submit it in Canvas. But if you've taken a class with me before, the format for the exams in this class is the same as in other classes, like 3-4 true false, 3-4 multiple choice, and then the rest free response. Any other questions about the exam or the study guide? Yeah, so question, what about like HonorLock and Zoom? How are those going to work together? You're going to use Zoom on your phone, right? And you're going to use HonorLock on your computer. The room scan will not pick up Zoom on your phone. The truth is, right, the reason we do this is because HonorLock kind of fucking sucks, right? I have a feeling that everybody here knows it's possible to cheat with HonorLock. So yeah, you're going to sign into Zoom on your phone. You're going to turn your phone's output volume down, not all the way off, but down. And you're going to set your phone up like on the side of your desk against a coffee cup or something where I can see your hands, your paper, your lap. And yeah, no, it's not going to cause you trouble with HonorLock. We will talk from time to time through Zoom. Like if there's something I need to say to the whole class during the test, I will say it through Zoom and that will come out your phone and HonorLock will flag it for sound. I will of course be reviewing the HonorLock videos, so you don't need to worry about those flags. Obviously I will issue those flags. So yeah, HonorLock will flag you from time to time due to the Zoom thing being open on your phone, but it will not interrupt the room scan. The room scan will still work fine. And the flags that come up because you're in Zoom on your phone, I will of course ignore. Yeah, the test is going to be on Canvas. The dates I put in there, so the question was the dates for the test in Canvas still say this Friday. I can change that now. The dates that are in the test in Canvas are approximate. I put those in based on the syllabus. So yeah, here. 11, 10 a.m. The true false questions will not cover any proofs, but they will cover concepts. A really good way to study for the true-false questions is to look at the textbook. At the end of each section here, let me show you. Let me come to like chapter 7 review, right? So if you look at the end of chapter 7, there's a chapter review in the textbook, and there are a bunch of like concept questions here, a bunch of true-false questions here. My multiple choice and my true-false questions are very, very similar to the multiple choice concept and true-false questions that you find in the textbook. So preparing for those, best way, look at the problems in the book. In addition to the chapter 7 review, a good place to look would also be the chapter 6 review, right? Because we did a lot of stuff from chapter 6. So again, make sure you are comfortable with these questions in the reviews. That is the best way to prepare yourself for the true, false, and multiple choice questions. Right, like this straight up. Almost every time I put this exact question on my test. So just, I don't mind telling you that shit. Look at the reviews. Other questions about the test, the study guide, how to prepare, what I need from you, what you need to do, that sort of stuff. All right, let me say it one more time. In order to get credit for the study guide, you need to submit scans of the written work for the study guide in Canvas. Solving the problems in WebAssign is not enough. I know it's really easy to type the correct answer into WebAssign. What I need to do is see your work. That's the purpose of the study guide, is for me to see your work and you to see my grading. So please, please, please remember to scan and submit the written work for your study guide in Canvas, and do it as soon as you can. If you can get the written work in by Friday, I can promise you written feedback before the test. That is my promise to you. Last call for questions. Okay, here we go. Partial fractions then. This is actually something that is supposed to be taught in pre-calculus. Can I see a react in Zoom? Thumbs up, whatever, any reaction in Zoom if your pre-calculus class discussed partial fractions. I'll be 100% straight with you guys. The last 2 times I have taught pre-calculus, we were not able to fit this in because things have been crazy lately. It's a kind of extra section that is not always discussed in pre-calc, but really should be. So it's one of the tragedies of the pandemic that partial fractions is one of those things that tends to get scrubbed out of pre-calc. We're going to go over it thoroughly since it looks like only one person has seen it before. Really, what partial fractions is a way to undo having a common denominator. The full name is partial fraction decomposition. And since that is quite a mouthful, I will often abbreviate this with the letters PFD. This is a process. It's purely algebra. This is a process to undo having a common denominator. Now we're going to use it to integrate functions. Of course, we're talking about techniques for integration. That's what all of chapter 7 is. But really, partial fractions itself is not a calculus technique. We're going to use this purely algebraic process to kind of pull apart rational functions into simpler little rational functions. The idea being, if you want to integrate the original big rational function, once you've pulled it apart into simple little pieces, you can just integrate each of the simple little pieces. To give you an idea what I'm talking about, let's combine these two fractions into one expression. I'm sure everybody here knows how to do this. I'm not trying to patronize you. Trust me when I say thinking about this will help you understand what we're about to do, even though this feels like a silly, way too easy thing. If I want to add these two very simple rational functions together, yeah, fine. If I want to add these two very simple rational functions together, the way you do that is by rewriting them with the same denominator. So this guy has a factor of x downstairs. This guy has a factor of x minus 1 downstairs. So I need to rewrite both of them with the factor they're missing. So the 1 over x is going to get multiplied by x minus 1 over x minus 1 plus the 2x over x minus 1 is going to get multiplied by x over x. And the result there is x minus 1 over x times x minus 1 plus 2x squared over x times x minus 1. And then you can just add the numerators. So you get 2x squared plus x minus 1 over x times x minus 1. And you could FOIL out the bottom if you wanted, right? That's x squared minus x downstairs. The question is, if I asked you to integrate this thing, you would look at me like, I don't fucking know what to do, as you should. But if I asked you to integrate this thing, you'd be like, oh, I know how to do that. This and this, they're both pretty easy to integrate on their own. So what partial fractions is going to allow us to do and I'm gonna use simpler examples to begin, of course, but what PFD allows us to do is convert something like the 2x squared plus x minus 1 over x times x minus 1 back into 1 over x plus 2x over x minus 1. Because integrating this thing is a little tricky, but integrating this form of it is much easier. Now, I will remind you a little bit how to integrate each of the sort of pieces over here. This one would just be a straight natural log. This one would require some long division, and then would be a little u sub. But that's the big idea. The big idea is that if I ask you to integrate a big fraction like this, the way you're going to do it is by splitting it up using partial fractions into simpler stuff like this. And the process for going from the big fraction to the sum of simple little fractions is called partial fraction decomposition. Okay. So I'm going to begin with an even simpler example. And then I will sort of show you the general case, and then we will look at some more complicated examples. This may end up taking 2 days to get through because there are like 4 cases, and the first one is very straightforward. The other 3 are slightly more complicated. The other thing, we're going to end up solving linear systems here, right? So we're going to end up with systems of linear equations that we need to solve. So you might want to remind yourself a little bit, matrix methods, elimination, all of that stuff. But this is the core idea. You can take something kind of complicated like this and use partial fractions to split it up into very simple stuff like this. And that's useful to us because if we want to integrate something complicated like this, we will split it up into the simple stuff like this and integrate the simple stuff instead. So I want to express the function f of x equals, let's do 2x over x squared minus 1 as a sum of simpler rational functions. I should be clear, I'll define it later, but a rational function is a ratio of polynomials. It's a fraction where the top and bottom are both polynomials. So this thing is already a rational function, but it's not as simple as it could be. Right? We're going to split it up into two simpler ones. The procedure in the gentlest possible case looks like this. First, you factor the bottom. So x squared minus 1 factors as x minus 1 times x plus 1. This whole procedure is really about the factors of the denominator. Then each factor of the denominator tells you a term in the expanded form. Look at the example we have up here. When we added 1 over x to 2x over x minus 1, we got a rational function whose denominator had factors x and x minus 1. Well, that's because of how adding fractions works, right? You find a common denominator and then you just add the tops. So each factor of the denominators of the expanded version contributes a factor of the denominator in the combined version. So if I wanted to go from here back to here, what I would do is I would start by saying each factor downstairs should get one of its own terms in the expanded version. I'll write it like this: a over x minus 1 plus b over x plus 1. So each factor of the denominator gets a term in the expansion. This line right here is called the PFD setup, the partial fractions setup. What we do from here is cross multiply to clear out the denominators. So on both sides, I'm going to multiply by x minus 1 times x plus 1. All right, we're doing the college algebra 1033 thing where you just want to get rid of the fractions. On the left-hand side, the x minus 1's cancel, the x plus 1's cancel, and you just get 2x. All right, so over here on the left, after I cross multiply, I'll just get the numerator, whatever that was. On the right, we need to distribute everything. So I'll take these two terms and I'll multiply them by the a over x minus 1. I'll take these two terms and multiply them by the b over x plus 1. A over x minus 1 times x minus 1 x plus 1. The x minus 1's cancel and you just get a times x plus 1. B over x plus 1, when you hit it with these two terms, the x plus 1's cancel, and you just get b times x minus 1. Every partial fractions problem will get to a line like this at some point. This is a line I like to give a name to. You can call it whatever you want. I will call it star. Right, it's an equation that I'm going to refer back to from time to time. Now from here, we're going to distribute everything on the right-hand side. So left-hand side stays 2x. Right-hand side, when I multiply that out, I get ax plus a plus bx minus b. And then we will combine any like terms. And I'm thinking about like terms as stuff with x's, stuff with constants. If there were x squareds, we'd combine all the x squareds together. This will give us 2x equals, I've got ax plus bx, that's a plus b times x. And then the constant terms are plus a minus b. I'll write that as plus a minus b in parentheses like this. I want to ask you a question kind of on the side over here. If 2x squared minus 3x plus 7 is equal to alpha x squared plus beta x plus gamma, what are alpha, beta, and gamma equal to? And I promise this is not a trick question. So we're gonna stop thinking about this for a minute and just come over here and think about this for a second. If 2x squared minus 3x plus 7 is equal to alpha x squared plus beta x plus gamma, what is alpha? Let's start there. Shout out or type in chat. Yeah, it's got to be 2, right? The coefficient of x squared on the left has to be the same as the coefficient of x squared on the right. Alpha would be 2. Beta? Beta would have to be -3. Very good. Right? Because the coefficient of x on the left is -3. The coefficient of x on the right is beta. Those have to match. And similarly, gamma would be 7. I'm going to apply the same logic to our bottom purple line over here. The trick is we're going to think about this as an identity between polynomials. So that left-hand side, 2x, I think of that as 2x plus 0. And the right-hand side is a plus bx plus a minus b. So by the same logic we just applied in black over there, the coefficients of x on the left-hand side and the right-hand side need to be the same. So a plus b must be equal to 2. And the constant terms on the left and the right also have to be the same. So a minus b must be equal to 0. And this is a system of linear equations. So this is how every partial fraction problem works at its heart. You set up the partial fractions, and choosing the correct setup, the original purple stuff here, is very important. I'll show you how to do that. Then you cross multiply by the denominators, distribute everything out, and collect your like terms. This you think about as an identity between polynomials the same way we think about this, which means you can set the coefficient of x on the left, which is 2, equal to the coefficient of x on the right, which is a plus b. I wrote that here as a plus b equals 2, just because it looks nicer with the a plus b on the left. You can set the constant term on the left, which is 0, equal to the constant term on the right, which is a minus b. So a minus b must be equal to 0. We call this equating coefficients. All right, we equate coefficients on both sides, and it's a very powerful tool. We can solve this linear system by elimination. And in general, you want to solve your linear systems either by elimination or using matrix methods. Elimination and matrix methods are kind of equivalent. If you have a big linear system like a 4x4, 5x5, definitely use a matrix. But here, if I just add the first two equations, then I get a plus a is 2a, b plus negative b is 0, so 2a equals 2. And we get this by adding the equations together. It's not always this easy, but when you add this first equation straight up with this second equation, you get a plus a, b plus negative b equals 2 plus 0. So 2a plus 0b equals 2, which is 2a equals 2. Divide both sides by 2, you get a equals 1. And then plugging a equals 1 back into either equation, you will find that b is, so here, let's do it. Let's sub it into the first equation. We get 1 plus b equals 2. Subtract 1 from both sides, and you get that b is also 1. We started off by saying 2x over x minus 1 times x plus 1 is equal to a over x plus 1, a over x minus 1 plus b over x plus 1. So now I can come over here and say, therefore, 2x over x minus 1 times x plus 1 is equal to 1 over x minus 1, because a is 1, plus 1 over x plus 1, because b was also 1. And that is the job done. If I asked you to integrate the thing on the left, you might go, I'm not sure how to do that. But if I ask you to integrate the thing on the right, you sure as shit know how to do that. It's 2 little baby u subs. And that's why we do this. Okay, so this is about as tame as these examples get. I'd like to take a second, make sure your notes are nice and clean, ask any questions that come up here, because things will get more complicated from here. Sorry, I see a question coming in chat. It's just not fully fledged yet. Not entirely. So the question is, what exactly am I doing when I plug this back in? So when you're solving a linear system, any linear system by elimination, once you get one of the variables, like here I found a, you can plug that back into either of these equations to find the other one. So what I did is I plugged a equals 1 right here. So I take the first equation, and I know a is 1, so I replace this by 1. That gives me 1 plus b equals 2, which is what I wrote here. And then I just solve that for b by subtracting 1 from both sides. So I subtract the 1 over, I get b equals 2 minus 1, which is 1. I could have also substituted it in here. Yeah, you only use one of the equations. Yep. If I plug a equals 1 in here, then I'd get 1 minus b equals 0. I could add b to both sides and get 1 equals b. That would have worked also. But yep, after you find a, you substitute that into either one of, but only one of, the original equations and solve for the other guy. A review of linear systems would be wise, right? Because the linear systems are going to get more complicated than this. But yeah, I would recommend using whichever one is easier. It's possible that you have more than 2 variables that you need to solve for, like a, b, and c. And in that case, you would want to make sure that you're very comfortable running the Gauss-Jordan elimination algorithm. So we'll work our way up. I'll show you some examples where things are a bit more complicated. I'll try to build up to this gently. So let's see if there's a case where we've got to go. I suppose we should do that first. Yeah, okay. Why not? Well, no. Let's do the other simple one first. This will be better. Does this guy factor into distinct linear factors? He does. Okay. So we're going to go ahead and do example 2 here. I'm going to write it down. I'm going to evaluate the indefinite interval of x squared plus 2x minus 1 over 2x cubed plus 3x squared minus 2x dx. Here it is. Okay, sorry, let me come back really quick. So we were equating coefficients. Remember the same sort of thing we did with this quadratic? I said the x squared numbers had to be the same, the x numbers had to be the same, and the constants had to be the same. I did that here. So the x's on the left, I had 2x, and the x's on the right, I had a plus bx. So a plus b had to be equal to 2. We do that with the constants also. The constant on the left, right, 2x, is the same as 2x plus 0. So the constant on the left was 0, and the constant on the right was a minus b. So a minus b had to be equal to 0. That's where that second equation came from. Bueno. All right. So we've been given a bigger task here. They want us to solve an integral. And it looks kind of fucking scary. We're going to do the same thing that we did on that last problem. We're going to take this function and express it as a sum of simpler rational functions through that same procedure we just used, partial fractions. Remember the core idea. The core idea is that in the expanded form, the terms come from the factors of the denominator. So what we need to do is first factor the denominator. Forget about the integral entirely. We're going to do no calculus through the first 10 parts of this problem. So upstairs, I have x squared plus 2x minus 1. Downstairs, I can first factor out an x. And what's left will be 2x squared plus 3x minus 2. And then I need to factor that quadratic. So my upstairs is still x squared plus 2x minus 1. I don't really give a shit about the numerator. You don't need to factor the top. I don't think that numerator even factors. The only time you would worry about factoring the top is if you think there might be a factor that cancels. But we do need to figure out how to factor this quadratic. So I take a times c, that's -4. I need two numbers that multiply to -4 and add up to +3. That would be +4 and -1. So I'd write this as 2x squared plus 4x minus 2. Let me do this off to the side. 2x squared plus 4x minus x minus 2, which I can write as 2x times x plus 2 minus x plus 2, which is 2x minus 1 times x plus 2. This is just the AC method. the factoring quadratic. So I get x times 2x minus 1 times x plus 2. Yeah, so I rewrote the middle term 3x as 4x minus x. That's the trick for factoring with the AC method, and then I factor by grouping. So again, if you need to remind yourself how to do this sort of thing, Google AC method, factoring with the AC method, or just factoring this quadratic. If you have another way you like to do that, that's fine. This is just how I do it. The next step is going to be the partial fractions setup. Which is where you take your function with the denominator factored, and you give each term from the denominator one term in the expanded form. So I'll write this as a over x plus b over 2x minus 1 plus c over x plus 2. And from here, everything is the same as we did last time. I'm going to show you a shortcut. So again, we need to cross multiply. When I so cross multiply meaning multiply by all three terms in the denominator on both sides. So I'm clearing out the fractions. When I do that, my left-hand side will have x squared plus 2x minus 1. When I multiply a over x by x times 2x minus 1 times x plus 2, the x's will cancel, and I'll get a times 2x minus 1 times x plus 2 plus. When I multiply b over 2x minus 1 by x times 2x minus 1 times x plus 2, the 2x minus 1s will cancel. So I'll get just bx times x plus 2. And when I multiply c over x plus 2 by x times 2x minus 1 times x plus 2, the x plus 2s will cancel. So I'll get c times x times 2x minus 1. This term is just a over x. This term is just b over 2x minus 1. And this term is just c over x plus 2. So every factor from the denominator gets one term here. And each of those terms is just a constant over that factor, a constant over that factor, and a constant over that factor. Yeah, then when I multiply this guy by these three terms, the x's will cancel. Right, so a over x times 2x minus 1 times x plus 2, the x's cancel, and I just get a times 2x minus 1 times x plus 2. Yes, the x cancels, exactly. And the same sort of thing is true for each of these, right? In each of these, one of the terms canceled. The term that was in the downstairs canceled here. The term that was in the downstairs canceled here. The term that was in the downstairs canceled here. This is the equation that I call star. So I want to make sure we're all comfy up to here. Any questions about how we arrive at this equation? Don't be shy. Okay. So if we were proceeding the way we did last time, I would FOIL everything out on this side. I would multiply everything out and collect all the like terms and equate coefficients, right? There's a faster way to do things. Instead of doing that, this is supposed to be an identity. This should be true for every value of x in the universe. I can plug shit in. I can plug some cleverly chosen values in for x. So if I send x to 0, what does that equation turn into? Well, on the left-hand side, I'd have 0 squared plus 2 times 0 minus 1. Let's write it. Equals. Here I'd have a times 2 times 0 minus 1. That's a times negative 1 times 0 plus 2. I should have just written 2. Sorry. Here I'd have b times 0 times 2. And here I'd have c times 0 times negative 1. Why is this so nice? These are both 0. My left-hand side is just negative 1. My right-hand side is a times negative 1 times 2. That's negative 2a. Divide both sides by negative 2. You get 1/2 equals a. So without ever setting up or solving a linear system, I was able to recover the coefficient a. This number right here is 1/2. This part is done. I now know that this is 1/2 over x, or 1 over 2x. I'm going to do the same sort of thing to recover the coefficients b and c. I'm going to plug in a particular value for x into the equation star. The way I choose those values of x that I'm going to plug in is by thinking about what numbers will make these factors 0, right? The reason I chose to send x to 0 is because this factor and this factor both go to 0 with x. So if I plug in 0 for x, these two go away, leaving me just this guy. But with numbers plugged in for x, with zeros plugged in for x, which means I can solve for a. Let me try next sending x to negative 2. As x goes to negative 2, the equation star becomes negative 2 squared plus 2 times negative 2 minus 1. Let's write it. Equals. Here I would have a times negative 4 minus 1 is negative 5 times 0 plus b times negative 2 times 0 plus c times negative 2 times 2 times negative 2 is negative 4 minus 1 is negative 5. And again, what you see is that 2 of these terms are going to be 0. So from this, we'll be able to solve for c. I need to clean up the left-hand side here. This is 4 minus 4 minus 1. So this left-hand side is again just negative 1. That's nice. This is 0a plus 0b plus 10c. So I get negative 1 equals 10c. Divide both sides by 10. You get negative 1/10 equals c. So far I have found a, this term is done. I found c, this term is done. I just need to find b. The thing I'm doing here has a name, by the way. It's called the Heaviside trick. And it is a good trick. Saves you a lot of time. I want a little bit of interaction from you guys at this stage. I was able to recover A and C by plugging in 0 and -2 respectively, because when I plug in 0, these guys went away. When I plug in -2, these guys went away. Is there a number I could plug in that will make this and this go away so I can solve for B? What number can I plug into this equation here, star, so that the A and C pieces go to 0, but the B piece does not go to 0? I got 3 hits in chat there really quickly. First, I want to mention that the public one, the one you guys can all see, is correct. Quinn and Tyler both nailed that. 1/2 is what we're going to do. One of the questions was, where did 0 and -2 come from? 0 and -2 were chosen, precisely like you said, to get rid of this term, right? These terms both go to 0 when you plug in -2 for x. And these two terms both go to 0 when you plug in 0 for x. So yeah, we're picking x values that make as many things as possible over here 0 at once. The way it works out, because we canceled one factor in each of these, if you plug in 0, all but one of them will go away, A. If you plug in -2, all but one of them will go away, C. And if you plug in 1/2, all but the middle term will go away, right? This factor, 2x minus 1, he is 0 when x is 1/2. So if you plug in 1/2 for x, this will be 0 and this will be 0, which will leave just this piece, allowing me to solve for B. So our final step here, as x goes to 1/2, equation star becomes, the arithmetic here is going to be a little bit more work. I'll have 1/2 squared plus 2 times 1/2 minus 1 on the left, right? Plugging in here, equals, this will be A times 0 times something else. I don't care. I'm just going to write A times 0 plus B. This is the one that isn't going to be 0, so we're going to be careful about this. B times 1/2 times 1/2 plus 2 plus C times 0, right? Because he also has the 2x minus 1 factor. So now we're going to clean up both the left and the right-hand side. 1/2 squared is 1/4. 2 times 1/2 is 1. 1 minus 1 is 0. So the left-hand side is just 1/4. The right-hand side is B times 1/2 times 1/2 plus 2. Well, 1/2 plus 2 is 5/2, right? 2 is 4 over 2. So this is 1/2 times 5/2, which is 5/4. And if you cross multiply or divide both sides by 5/4, however you want to think about it, solve for B, you will get 1/5 for B. And now here we have A, B, and C. There's a good question here in the chat. So could we, if we wanted to, could we go back and after finding A and C, 1/2 and -1/10, we could go back in here, plug in 1/2 and -1/10 for A and C, and then solve for B doing the stuff we did before? Yes, you could. Yes, you could. It would take more time. It would take more time than what we're doing here. In fact, all of the bracketed work down here is optional. You could solve this whole problem the way we solved the last one, where you expand everything out and set up a linear system. And there are instances where you'll have to do at least some of that. But what I'm showing you right here is a shortcut called the Heaviside trick that allows you to avoid doing all that work. So yes, absolutely, Juliana, we could take these, plug them back in here, and then try to solve for the missing guy by setting up a system. Or we could have started by setting up a system and then solving it. It would be a 3x3 system of equations. But this is generally faster and easier. So wherever possible, I invite you to use this trick. All right, we're almost done with the problem now. We said that my function is equal to a over x plus b over 2x minus 1 plus c over x plus 2. So the integral of my function over what is x times 2x minus 1 times x plus 2 is equal to the integral of a over x. So what was a? A was 1/2. So this is going to be 1/2 over x plus b over 2x minus 1. B was 1/5. So this is 1/5 over 2x minus 1 plus c over x plus 2. And c was negative 1/10. So after you do all the partial fractions work, you set up the partial fractions, you cross multiply, you do whatever you need to do to find the constants a, b, and c. What I showed you here is my favorite trick, fastest way I know of to do it. Then you go back and you write the integral. Now the integral of this thing on its own as it's written is fucking scary. I don't know how to do it. I do know how to do this. I do. I can split this up. 1/2 integral 1 over x dx plus 1/5 integral 1 over 2x minus 1 dx minus 1/10 integral 1 over x plus 2 dx. The first one is easy. How do I do the other two? Let's focus on this guy. How do I do the middle integral? Let's see how I'm doing on time. Very good. Yes, very, very good. Thank you. These both require a little substitution. So in the first guy, I would let u be 2x minus 1. du is then 2 dx. In this guy, I would let z be x plus 2. dz is just dx. So this first guy is going to be 1/2. I'll leave it as it is as an integral for now. We'll do all the integrals at once. The 2 here tells you that dx is 1/2 du. So I'll write this as 1/5 times 1/2 times the integral of 1 over u du. And we've got minus 1/10 here. dz was just dx, so this will just be integral 1 over z dz. So it's often going to be the case that you have to do multiple little substitutions at the end of these problems. Use different letters. Don't use the same letter, you'll get confused. Now we're ready. This is 1/2 natural log absolute value of x plus 1/5 times 1/2 is 1/10 natural log absolute value of u minus 1/10 natural log absolute value of z plus a constant. And then finally, we plug back in 1/2 natural log absolute x plus 1/10 natural log absolute value 2x minus 1 minus 1/10 natural log absolute value x plus 2 plus c, and you are done. Took a minute, right? Not a fast problem. 2 pages. There's really no getting around it. That's as short as you can do it. If you wrote it out, like, finding your linear system and solving that, it would be more. This is the quickest way I'm aware of to integrate this function. It's just how it goes. Integration is harder than differentiation. Yes. Okay. Comment in chat. Some people write log instead of ln. So the convention I adopt is that I will always write ln for the natural log. Log usually means the common log, the base 10 log. Ln means the natural log or the base e log. In some fields, like where I work in number theory, we actually write log for the natural log because we don't fuck with anything other than the natural log. Base 10 logs don't mean anything to us in number theory. And there are some other fields that are like that. But for us, the integral of 1 over u du or 1 over x dx is always ln of natural log, base e log. Yeah, log, some people use for the natural log. We won't do that. Log for us means the base 10 logarithm. Always use ln, yeah. Any other questions on this one? Well, you see, the calculus wasn't very hard, right? All the calc is right here. The vast majority of this work was algebra. We had to factor a 3rd degree polynomial. That's a bit of work on its own. Then we had to set up the partial fractions and do all this shit to find the numbers a, b, and c. And this really is the fastest way to find the numbers a, b, and c. Unfortunately, it doesn't get better from here, it gets worse. This problem still fits into the category of like nicest possible partial fractions problems. So a fact about polynomials. Not all polynomials can be factored into linear terms over the real numbers. Right? If you had a good pre-calculus class, then you learned that using complex numbers, you can always factor a polynomial down into linear terms. But it is possible. So let me go ahead and describe to you partial fractions in general now. Oh, I want to see this. So partial fractions is an algebra process for expanding rational functions, I should say proper rational functions, like f of x equals p of x over q of x, where p of x and q of x are polynomials. The word proper here means that the degree of the top is strictly less than the degree of the bottom. Expanding these things into a sum of simpler rational functions whose denominators are the factors of Q of X. If your rational function is not proper, you cannot do partial fractions. And I'll tell you what to do if you don't have this. If the degree of the top is equal to or larger than the degree of the bottom, you need to do long division. So you gotta remember how to divide polynomials. I'll give you an example before we leave. The factors of Q, so here's your PFD Bible. Right, just like your trig sub Bible. Here's your PFD setup Bible. And on the left-hand side, you have Q of X has a factor like this. And over here, your PFD setup will contain. If you have a simple linear factor like AX minus B, then your PFD setup will contain a term like A over AX minus B. It's possible that your denominator has a repeated factor like X plus 1 quantity squared. It could be raised to the third power or fourth power. In those cases, you need to build up to that power. So you'd have something like A1 over AX minus B plus A2 over AX minus B squared plus A3 over AX minus B cubed. You build up to whatever that multiplicity is. So if you have X minus 1 cubed in your denominator, that single factor is going to contribute 3 terms to the partial fraction setup. These are called repeated linear factors. You could also have an irreducible quadratic factor downstairs, like X squared plus 1. That doesn't factor, not over the real numbers. If you have an irreducible quadratic, then you'll need to give it a linear numerator. And the worst possible case is a repeated irreducible quadratic. And here you kind of blend the two. You're going to have to build up to that multiplicity, giving each piece a linear numerator. I'll show you examples. Yeah, so A1x plus B1 over AX squared plus BX plus C plus A2x plus B2 over AX squared plus BX plus C squared plus out to, so AMX plus BM over AX squared plus BX plus C to the n. If you try to write out the full rule for partial fractions, it looks terrifying. This is the closest thing to writing out the full rule I can give you that is still like tractable. If you look at the Wikipedia page for partial fractions, the formulas there are quite frightful. In the time we have left here, which is not much at all, in fact, I think we're actually out of time, I would like to look at one of these second case problems. At least show you the setup, okay? I'll give you a minute to write, take a screenshot. This stuff we will save for Wednesday, okay? But before I let you go, I want to at least look at the setup for a problem like this. If you need a screenshot or whatever, grab it. I'm going to turn the page in just a few seconds. Okay, here we go. So I want to find the partial fractions setup for this function, x minus 1 over x to the 4 minus x squared. We need to factor the denominator. So that'll give me x minus 1 over, there's a common factor of x squared I can pull out there. And what's left is x squared minus 1. And then x squared minus 1 can be factored. Oh, this is interesting. Let me change this to x minus 10. Sorry, just to avoid a silly thing. I'm going to change this to x minus 10 upstairs. X minus 10 upstairs. I'll have x minus 10 divided by x squared times x minus 1 times x plus 1. Otherwise, the x minus 1s would cancel. You could do that too, be okay, but I just want one thing at a time. So here's the denominator fully factored. These two are simple linear factors, but x squared is a repeated linear factor. That's x minus 0 all squared. So your partial fractions setup, if you follow the rule that I just wrote out for you here, if your denominator has a repeated linear factor, you need to not only have that power downstairs, like it's not going to be just one term that comes from that, you're going to have a bunch of terms that come from that. In this case, the x squared term in this expression will contribute an a over x and a b over x squared, just from this one term downstairs, because you have to build up to that power. Then we would have plus c over x minus 1 plus d over x plus 1. And the new thing here is the two terms coming from this repeated factor. If this was an x cubed, there would be three terms coming from him: a over x, b over x squared, c over x cubed, then d over x minus 1, e over x plus 1. Okay. So that's it. That's our PFD setup. Yeah, really quick, let's go ahead and entertain this idea. Let's do x to the 4 times x minus 1 times x plus 1. Same thing. So if you factored your bottom and you got something like that, the setup here would look like a over x plus b over x squared plus c over x cubed plus d over x to the 4 plus e over x minus 1 plus f over x plus 1. Yeah, this is the good question, right? So first, let me make sure we're all on the same page. All four of these terms came from this one repeated factor downstairs. Why? Why do I need four terms for this? Why can't I just say d over x to the 4 and fuck all these guys? Well, what happens if you add two things that look like this? Or three things that look like this? Or four things that look like this? The reason you have to include all of these wouldn't change the denominator. Yes, it's possible that this function came just from 3 terms that look like this. If you add 3 terms that look like this, you will get something whose denominator is this. But it's also possible that something with a denominator like this came from adding all sorts of shit like this up. These first 3 terms here, because they are the same factor as this guy, just lower multiplicity, would not contribute anything new to the denominator. In other words, it's possible to get something like this by adding up maybe 1 over x and 5 over x to the 4 and 2 guys that look like this. We don't know ahead of time whether this x to the 4 came just from 1 term like that, or from maybe 2 terms like this and 1 like that. If you were to go out and solve this problem, I bet you would find that some of these guys are 0. Probably not all of them, but probably some of them. In fact, my suspicion, just looking at it, is that these 2 are 0. This is not 0, and this is not 0. Of course, these would be non-zero. My guess here is if you actually solve this particular random problem that I just made up, is that C, D, E, and F would be the non-zero guys, and that A and B would be 0. But the point is, from this function, you cannot tell. You cannot tell if that x to the 4 came just from a single term with an x to the 4, or a combination of lower order terms and one of those. This is why you have to build up. Think about, and I'm going over time here, so I'm going to stop. Think about 1 over x minus 2 over x squared plus whatever, 3 over x plus 1. If you actually add these up, you get x over x squared minus 2 over x squared plus 3x over 3x squared over x squared times x plus 1. And that would be x times x plus 1 2 times x plus 1 plus 3x squared over x squared times x plus 1, which is, let's see, x squared plus 3x squared is 4x squared plus x minus 2x is minus x minus 2 over x squared times x plus 1. All right. If I gave you this thing, you might think that in its expanded form, there is no 1 over x piece, just something over x squared and something over x plus 1, but that's not true. The way I came up with this was by adding these 3 things together. So this 1 over x term is kind of hidden in the final form. I hope that that clarifies why we need these earlier terms in the expansion, because they may or may not contribute something to the final form here. You cannot tell from the combined form whether there was just a 1 over x to the 4 piece or lower order things as well. Like here, there's a 1 over x piece and a 1 over x squared piece, but you can't tell looking at this final form of it. So that's the deal. These are the first 2 cases for partial fractions, and I invite you to go ahead and try to solve this guy. See if you can find A, B, C, and D, or just take a look at the homework. I'm going to go ahead and post your homework set right after this. Next time, we will look at more examples of partial fractions where we deal with repeated linear factors and also the irreducible quadratic factors. Is there anything you guys would like to ask before we wrap up for the day? Alrighty then, I'm going to go ahead and end the meeting. I hope you guys have a lovely rest of your day. The study guide is up. I will be posting your homework in the next few minutes. Take a look at the study guide. You can solve some of those problems. Try to get that stuff into me by Friday, and then work on the homework. That is it. Take care.